Welcome students. In this video, we are going to talk about the complex plane and some of its properties. So the first thing first, let's just understand that what we have here is, first of all, what's a complex plane, right? So C, this is what we defined, right? And how did we define it? We define it as the set of all x plus iy, okay, where x and y are real numbers, okay? And what is I? I we have defined it as root over minus 1. Okay. Now with this thing, so C is the whole set which we have. I want to talk about just a point set in C. So what is a point set in C? Whenever I say a point set in C, what does that mean? It means you are taking collection of finitely many or infinitely many points. So essentially it's the collection of finitely many, of finite or infinite, finitely many or infinitely many or infinitely many points of C. Okay, points of C. So basically what I am saying is this: you take some points of complex numbers, put it together in a set, and then that we will call it as a point set. Yes. And as an example, very easy this one. As an example, let's say you take the number 1 as a complex number and I. So that is a point set. Yeah. You can also think of your the unit ball. So basically what x plus iy, basically this set such that mod x plus iy is less than equals to 1, let's say. Yeah. So essentially the unit disk along with the boundary of it. Yes. So that also we can think of it as a point set. So all of these are point sets. So this is a finite point set, that's an infinite one. Okay. And there are tons. I mean, you can build your own. Okay. So with that being said, first of all, see, in this video, we are essentially trying to first look at how complex numbers can be viewed, complex planes can be viewed. So, for this course, essentially, we will deal with this thing that C over R. Okay, this is what we are going to work with, C over R. What do I mean by this? So basically, this is a set, right? This is a point set. C also is a point set of C, of course, yes. Now, what we want is this C, we want to look at this C as a vector space. Yes, if you don't know what vector space is, please go back and look at your linear algebra thing if you have forgot it. So C over R, we want to talk about that. So what is it? So this is a vector space. How is it that, so let's say that A plus IB and C plus ID, yeah, these are two complex numbers, complex numbers. Now we have already talked about how to add those two numbers, right? So we can do this: A plus IB plus C plus ID, the complex addition which we already did. So that is what it is: A plus C plus I, B plus D. Yeah. So you have this addition. So this is like you can think of as a vector, and we can add those two numbers. So essentially this is addition operation of vector space. And so this is A. Also, what is B? Or maybe I should not write A. I should write, this is the first one and the second operation. So this is the addition. This is the addition. Okay, now I want a scalar multiplication. So let's say lambda is in R, yeah, and A plus IB is a complex number. Yes, that will imply that, can we say this, lambda times A plus IB? What does that mean? So this is the scalar multiplication. What we are going to do is we basically multiply that lambda with the real and the imaginary part. So it becomes lambda A plus I times lambda B. Yeah. So if you define it like this, so basically the scalar multiplication, you define it like this, and the addition you the addition you define it like this, then this is the scalar multiplication. Then what happens is you can actually show that C over R, this particular set. Yeah. So therefore we can show that C over R is a vector space. Okay, vector space. Yes, please check this part. Check this. Okay. Yes, and of course, if it is a vector space, the natural question is what sort of dimension are we looking at? Here, the dimension is exactly 2. The dimension of C over R is 2. Okay, so what is the basis of this? Basis is 1 and I. Yeah, what do I mean by this? So, as a small remark, we mean that any element, we mean that what is the the basis means. So let's say Z equals to A plus IB is in C, right? So you can write, you see, Z can be written as A dot 1 plus I dot B, right? Yes. So the coordinate basically of Z is AB. That's what it means. Huh? So see, we can write it using this basis vector 1 and I. So that will be your your dimension 2. Okay. Okay. So essentially what we are saying is you take any two elements of the complex non-zero element basically of the complex plane. So in this case I am taking 1 and the other element is I, and what we showed is any element Z which looks like A plus IB, of course any complex number looks like that, then you can represent those using the scalar multiple A and B. These are in R. A is in R and B is in R. So essentially, in this case, dimension is going to be okay. Now, a very important note. You should always understand that C over R is the dimension 2. You can also do the similar sort of vector space. You can actually define C over C. So essentially what I mean is this scalar which you are multiplying, that can be also a complex scalar. Yes, but the thing is everything changes according to that. Yes, and what happens is this you can show that also forms a vector space. Okay, space, but it's a different kind of vector space. The geometry, the analysis is very different. C over C is a vector space of dimension 1, and what is the basis element? You take a non-zero, let's say 1, that will be your basis element, because you see, if you take Z in C, yeah, then you can write Z equals to Z times 1 here. Yeah, so you see any element, so you see this 1, that's the basis element. Yes, so you can write Z times 1, and hence this is any element can be represented using this basis element. Yes, and in this case it is true because see, Z is already in C. So this is always true. So you see, in this case, what is happening is C over C is a vector space of dimension 1. Yeah. Now, please remember this thing, and let me put it in maybe a red color. Yeah, it will be better. So in this whole course, we will always assume C over R. So all these analysis which we are going to do for the rest of the course, we are always going to assume that C is over R. This is the vector space. This is our assumption, C over R. Clear? Yeah. I will explain to you why exactly do we need this assumption. Yes. So I will explain to you later. For now, we will always assume C over R. Yes. So essentially, it's a two-dimensional vector space if you think about it like that. Okay. Right. So with that being said, so we have a point set. We know it's a vector space of dimension 2. Of course, a real vector space of dimension 2. And that's what I am trying to say here. Okay, so now we'll define a very important concept, the concept of an open set in C. Yeah, this is very important, and this is like the cornerstone of this whole theory. We need to understand what these particular, objects mean. Yes. Okay. Sorry, not in R, in C, sorry. In C. Okay, so what does it mean? It means that let's say that S, yes, this is a set. Yes. So a set S is open in C. Yes, open in C. This is very important. Where is it open? Yeah, in where? What is the ambient? So basically, you see, think of this. Let's say this is your C. Yeah, of course, you can't write C like that, but I mean, it's a plane, right? In our case, because C over R, right? It's a two-dimensional plane essentially. But the thing is, let's just pretend that this is your C. Now the thing is, that's your S, the set S. Yes, I want this set. I will call this set as an open set. But when can I call this set as an open set? When, you see, if you take a point in this set, yeah. So you see, S is open in C. So this set is open in C. Yeah. If for every point in S, so if you take a point in S, okay, so has a neighborhood, okay, has a neighborhood. I will explain to you what neighborhood means. Lying entirely in S. Okay. So what do I mean? See, whenever I'm saying neighborhood, that is, what do I mean by this? Mathematically speaking, there exists an epsilon greater than 0 such that, okay, the ball containing the point. So let's say Z naught. Huh? So every point, let's call it Z naught. Huh? A Z naught point which is in S. So let's say this is Z naught which is in S. So B Z naught epsilon. Yeah. This should always be contained in S, totally contained. Yeah, not outside or the boundary. It should be totally contained in S for some epsilon. Yeah, I mean, it doesn't have to be all epsilon. Of course, that's not true. But the thing is, some epsilon. You can show a small enough epsilon. Yeah, for that, for which this is always true. Okay, right. So what do I mean by this? You see, whenever I'm saying the ball, so what I meant is B Z naught epsilon is, by our definition, if you remember, our definition is set of all those complex numbers Z such that the distance between Z and Z naught should be strictly less than epsilon. Okay. This is where this is our definition. This is what definition I'm using. Yeah. So what do I mean by this? I meant that let's say Z naught is this point. So essentially I am looking at all those Z's which lie within the epsilon radius of this ball. Yes, I hope this is clear. Yeah. So you have to have this is always true. Yeah. So if this is true for every point Z naught in S, then we call that set as an open set. Yeah. Okay. So what are the examples? Let's look at examples. So of course, the first example is this B Z naught, let's say 1. Yeah. The radius 1. That is of course an open set. Yes, you can see that that is always true because if you take any point in this, ball, yeah. So essentially, what is this? Let's say Z naught is, for now, let's just assume Z naught is the origin. Yes. So unit ball. So we are looking at this disk. Yeah, this is the disk, not the ball. Sorry, this is the disk. Yes. So in this disk, if you take any point, yeah, Z. So let's just assume it like this. See. Let me draw it here. Let's say that this is your unit disk. Okay, this is your unit disk, and so we are taking every point inside this, not on the boundary. And let's say Z is any point here. Yeah, of course you can put a ball which lies entirely within this set. Yeah, so how do you do it? You see, you take the distance between Z and origin. Yeah, or to the boundary, and you take half of that and build a ball which is totally contained in here, so you can easily show that, right? So please do that. So check this part, okay. Okay, fine. I hope you understand what I'm trying to say. See, from here to here the distance is mod Z. Yeah, and from here to here the distance is 1, right? Okay, so what you can do is, so from here to here distance, the straight line distance is 1 minus mod Z. Yeah, so you divide it by 2 or by 9, 10, whatever, some number, right? Such that from, so there is a ball which is this will be your radius. This will be your radius. That radius ball will be totally contained here. So please do that, check it. Okay, let's look at the second example. So let's say that we define the upper half plane, or the right half plane, doesn't matter, upper half plane. Let's just define it like the upper half plane. So what is it? It is set of all those y greater than 0 such that x plus iy So this is in C, of course, right? X plus Iy is in C. I am just looking at the set where y is positive. So let's just look at what is this, how does it look like? This is A. Huh? The B looks like this. You see, this is your y positive. Y is always positive in this area. Yeah, this area. Y is always positive. Yeah. So essentially, your upper half plane looks like this. This part. Yeah. That is also definitely going to be open. So this is also is open. Yeah. These also you need to check. So please check these parts. Huh? These are very simple. Again, let's say you start a point Z. Start from a point Z. Yeah. How do you show that this is open? Again, the distance between this and this, you have a distance, right? Yeah. So what you do is you take a ball of radius which is less than half of the distance, and that ball will be totally contained in this set. So you have to show that, but this is not very difficult. You can of course do it. Yes, that's a set. Okay. Now, if I change this, yeah. So you see, if I change this set to this set, y is greater than equal 0. Okay. Greater than equal 0. Such that x plus iy is in C. So essentially, I am looking at the point such that y is positive. So essentially, here what I am doing is I am taking every point in this part. Yeah, everything. So everything in the upper half plane plus where y is 0. So y is 0 is in this line, right? The real line. So the real part of z, that has to be contained here, right? Yeah. So that is basically 0 in this part. So essentially, this is not open. This is not open. Yeah. Why is this not open? Of course, this is not open because any point here, you can show that there is a small neighborhood around that point which is totally contained in the set. But what about any point? Let's say you take any point on the boundary here. Yeah. If you take any small neighborhood, doesn't really matter how small, you are always going to end up with some part totally outside this set. So these points are not in this set. Yeah. So this is not a open set. Yeah. I hope that you can write it down. Yeah. Please make sure that you write down this exact thing. What exactly do you write mathematically? That's what I'm trying to say. Yeah, please write it down. So you take any, so you, in this case, what you do is you take any epsilon ball. Yeah. So let's say this is your Z naught in this case. So take any epsilon ball, B epsilon Z naught, and you show that there are always points on this ball. Yeah. Since Z naught, how does it look like? It looks like the imaginary part is always equals to 0, right? For Z naught, the imaginary part is always equals to 0. So this is basically, I mean, just the real part is there. Huh? So X is there. So it will be in R, right? It will look like this. Okay. So now you can show that in this ball, there is always, so if you take this ball, there is a point here in this ball which lies outside this set, this particular set. Yes. Okay. See, again, I am not explicitly showing you how to prove it. Please do this. This is very simple. Use your ideas. Whatever I have described like this, use these ideas and you can actually show it. So that's the idea of an open set. Yeah. Of course, we are also going to define something called a closed set. Closed set in C. In C. Yeah. How do I define the closed set in C? So closed set in C is basically S is closed in C, is closed in C. Please remember, I am saying closed in C, yeah, not in other set, closed in C. If C minus S, so basically the complement of S, yeah, is open. Okay. So in this case, in our C, this definition, you see the complement of this. So you see, for example, okay, let's consider this set. S is Y less than equal, sorry, greater than equal 0, greater than equal 0, this set. Yeah. So this is the upper half plane with the boundary. Yeah. And what is C minus S? C minus S, if you look at it, this will be the set of all Y strictly less than 0. So basically the lower half plane, this part. Yeah. And this part, exactly the similar sort of thing analysis which you can do earlier we did. So you can show that this is going to be open. Yes. So since this is open, that set is going to be closed. Yes. I hope this is clear. Okay. So this is the first example. Let's look at a second example. So let's say I look at this thing B0, 1. So basically radius 1, center 0. Yeah. So by definition, what is the definition? And I am writing a bar here. Bar means this is the closure. I will call it a closure. So this is just a name. For now, we don't look at much analysis. We will do it like this. So we'll just define this thing as a closure of the ball with, sorry, closure of the disc. Closure of the disc. I should define it like closure of the disc with center 0 and radius 1 and radius 1. How do you define it? This is nothing but the set of all those complex numbers such that mod z is strictly less than 1. Clear? And then the closure will be this, the boundary is also included. So what do I mean by this? You see, earlier we are only looking at the inside of this. Now we are looking at the inside along with the boundary. So all this boundary point is also included. Clear? So in this case, that will be this is a closed set in C. Set in C. Why is that? Because you see, if you look at the complement of it, the complement of it is this. So what is the complement of it? Since S minus B01, the bar of it, yeah. So what is it? That complement is nothing but set of all those z in C such that mod z is greater than 1. Clear? So this is what? This is a open set. Open set, so the complement is going to be closed. Yeah, I hope this is clear. Okay. Now, these are the general, kind of sets which we are really interested in this course. There is other, very, very complicated sets you can draw. So let's say if you can build something like this, let's say, so let me put it this way, in a caution. Yeah. So let's put it this way. So let's say this set S is Q plus IQ. What is Q? Q is the rational set of all rational numbers, rationals. Okay, I'm not writing it properly, but you understand, right? It's a set of all rational numbers. Okay, now you see this set S. So the question which I want to pose is this. I want you to answer this. Is S open or is it closed? Okay, is it open or is it closed? Okay, so this is the only question. So that's the only question which I want you to answer, and I will give you a hint. Hint. Just think about it this way. Let's say that you start with 0, 0, right? So 0, 0, 0 plus I0 essentially, 0 plus I0, which is 0. Yeah. So the origin 0 is in S. Yeah. If you take a small ball B with center 0 and radius epsilon, doesn't really matter how small epsilon is, epsilon greater than 0, small. Okay. If you start with this thing, now you see this ball will contain element like a very, very small element, a rational, irrational. So let's say some irrational number A, B. Yeah. This will be always contained in B0 epsilon. Yeah. Such that, so this is A plus IB. If you want, you can write it like A plus IB. Yeah, this will be there. And how do you guarantee that this is always, this is there such that A and B, these are irrational. Yeah. And mod of A plus IB is strictly less than epsilon. You can always do that. So what I'm trying to say is this. You see, let's say this 0, 0 is a number, it's a point in S, right? So if you take a small enough, disk, epsilon disk, yeah, radius epsilon. Now, you see, you can always have a rational number which looks like A plus IB, such that A and B are both rationals. That element is not in S, right? But the length of that element from origin can be always made less than epsilon. Yes. If you have to explicitly find such an element, how do you find it? You just start with a rational number. So let's say pi plus I pi. That is a number which is not in S. So after that, you just scale it in such a way that it actually goes down beyond this, ball. and then you can actually show that that point is not there. That's the irrational which is not there, and then you are done. Clear? So of course you can do that. So again, please check this part. I want you to check this part. So this you have to do it yourself. Check, very important. Yeah, but generally speaking, we are not going to be very interested in this sort of sets in our course. I will tell you exactly what sort of things we are mostly interested in. So essentially, there is a very, very important concept in complex analysis, which will call as the connected set. Connected set. Huh? And here there is a little confusion. Sometimes people get confused here. So let me phrase it here in a certain way, and then we are going to rephrase it later. Yeah. So a set S is connected. Okay, if any 2 points in S, okay, can be joined by a chain of finitely many line segments in C. Line segment means basically the line segment has to be totally contained in C. Huh? Line segments, and it should always be contained in S. Okay, there are finitely many line segments, and sorry, I should write it like this: all of whose points are contained in S. Yeah, I am going to rephrase this thing later. We don't have enough ammunition to attack this exact definition properly, but we will do it later. But right now what you need to know is what sort of sets are connected essentially. So let's say example. I have to clarify this thing, what I mean by line segments, but let me give you some simple line, because you have some idea of what line segments is. Not probably a mathematical idea, but some idea. So what is the first example? The first example which we have is B0, 1, or it's not 1, that doesn't matter, some point with a radius 1, that ball. So essentially, what is that set? It is the set of all those Z in C such that the disk less than 1. So this is the disk of radius 1. Centered at origin. So this is connected. This is very simple to see. Yeah, because if you take any 2 points on a disk, what happens is you can take a straight line joining those 2 points, and that straight line will be totally contained in B. So basically what I am saying is this. See, let's say this example. Let's take this B0, 1 minus B0 half. Yeah. So what is this? This is essentially you are looking at something like this. This is an annulus. So essentially this is the part which you are interested in. Okay. So by definition, what is this? This is the set of all those Z in C such that, how do I put it? It is basically mod Z is greater than half, less than 1. Yeah, I will put it this way. I hope this is clear. Yeah. Maybe I should put it like bar, the closure of it. Yeah, this will be better. Okay, so essentially what I am doing is I am looking at Z, which is whose distance is strictly greater than half, but always less than 1. So this set, this is called a annulus in C. And this is also connected. Why this is connected? Because you see this, if you take any 2 points, here and here, any 2 points, yeah, you can always connect it using a straight line. If you take a point here, and let's say you take another point here, but there is this big hole outside, what do? You see, you connect it using some other points. You take other point here, you take another point here, and you take another point here, you can actually reach it. So essentially you see finitely many line segments, okay, to reach that. So this is also a connected set in our example. Okay, let's take another example. Let's say the real part of Z, that particular thing. So essentially what we are going to do is this set S. So let me write it this way. Sorry, let me write it this way. So S is a set of all those Z in C such that the real part of Z, which is X, is positive. Is positive. Yeah. So what does that set looks like? X is positive means this particular set. Yeah. Is this open? This is an open. This is open. Yeah. And is this connected? Of course it is connected. This is very simple to see, right? This is always connected. Okay. Now let me give you an idea of what line segment means. Line segment. And this is why you see we need the idea of complex over R, the two-dimensional complex thing. So line segments. See, what we do is basically what these are line segments. So basically we say L, let's say L. This is a set. So basically we are looking at a set S. A set S. A set S is called a line segment. Called a line segment. Okay. If so, how do you put a line segment? So basically, let's say if Z0 Z1 is in S, then lambda times Z0 plus 1 minus lambda times Z1 is also in S for 0 less than lambda less than 1. So essentially what I am trying to say is this. You see, let's say this is a line segment, yeah, so straight line. So you take any 2 points in the complex plane, Z0 and Z1, then the any point in between Z0 and Z1, that should always lie on S. Yes, that is what our definition is. That is what we are going to use as a line segment. Okay. Okay, so I hope this is clear. Yeah, so you have to have a finitely many line segments. You can join any 2 points using that, and then that definition we are going to use it as connected set. We are going to modify this definition into much different one. I mean, not a very different thing, basically with a path. But right now we did not define what a path is, and so we are going to do it later. So some modification is there. Okay, now we define something called a domain. Very important. This idea is very important in a complex thing. What is a domain? So a domain is a open connected set. Any open connected set is called domain. Open and connected set and connected set is called a domain. Okay. Yeah, in our case, whenever we are saying in complex analysis domain, we always mean an open and connected set. So what is an example? Example A, let's say the set of all those mod Z less than 1. So basically the open disk, that's a domain. Yes. Okay. The annulus, let's say half less than mod Z less than 1. That's a domain. So these are all example of open connected set. So these are domain. Okay. So these are domain. Right. Let's say this set mod Z equals to 1. What is this? This is the boundary of the disk. Boundary of the unit disk. Of the unit disk. Right. Now, of course, you understand up from now that this is basically a closed set. Closed set. So by definition, there is no question that whether this is a domain or not. It is not, because this is by definition a closed set which is not open. So essentially, that's a not a domain. Clear? Okay. Right. So that's those things are not domain. Yeah. So what, see, whenever I'm saying boundary, what I meant by this, let me just clarify a little bit and then we will be done. Okay. So first of all, we are going to define something called a boundary points. Boundary points. Okay. What are boundary points? So essentially, let's say a boundary point, boundary point of a set S, point of a set S, okay, is defined as a point Z0, let's say a point Z0, such that there is a neighborhood. Every neighborhood not there is a neighborhood, sorry, every neighborhood, NBD, I am going to write neighborhood as NBD. So every neighborhood of Z0 must contain points, okay, that belongs to S, and points that does not belongs to S, Yeah. So it is quite clear. See, if you are taking a disk, let's say, or in this case, it is this particular boundary of the disk. So we are basically looking at this thing. Forgive my drawing, it's not very good. So let me put it this way. Disk. Yeah. Now the boundary is basically we are just looking at points which lies on this ball. So mod z equals to 1. Okay. Now you see, you take any point here Z0 and you take a small enough neighborhood. Doesn't really matter how small neighborhood you take. You can always end up with points which lies on the set. And see, these points lies on the set and these points lies outside the set. Okay. So example mod z equals to 1. Yeah. For this example, every point is a boundary point. Every point. So if your set is mod z equals to 1, every point of the set is a boundary point. Set is the boundary point. Boundary, I will write it like the BDRY point. Okay. Let us look at more examples. Let's say B. Mod z less than 1. Yeah. In this case, no point is a boundary point. No point is a boundary point. Is boundary point. Why? Because you have already seen that any point in this thing, you can always get an epsilon neighborhood which always lies within this set. But here you have to have every neighborhood. You see, there is some neighborhood which should contain points in S or outside S. Okay, so that's no point is a boundary point. What about mod z less than equal 1? Yeah, see, these has points. Mod z equals to 1 are the points which are boundary points. Okay, so this set contains boundary points but interior points also, which are boundary points. Okay. Now if you put all this together, so the set of all boundary points, we will call it a boundary points of S is called the boundary of S. It's called the boundary of S. Okay, and we will denote it by as we throughout this course we are always going to denote it by del S. Okay, so this is boundary of S. Okay, for example, in this case, so let's look at small example. S is a set of all those Z in C such that mod Z less than equals to 1. Yeah. So the closure of the disk of unit disk. Let's look at it. Okay. So what is the boundary? So delta S, what is it? Del S is the set of all those Z in C. As we have already discussed, it is mod Z equals to 1. Yeah. That is the boundary. Okay. Right. And I will give you a small exercise. Okay. So this is an exercise. So just look at it. So let's say define A is a set of all those Z in C such that X, so real part of Z is positive. Yeah. Or real part of Z is negative, let's say, less than equals to 0. Find whether okay, A is open, closed, connected, and also find what delta A is. Okay, so please do all this and then you will have a very good idea of what boundary open sets, connected sets are. So with this, we are going to end this video, and essentially we are going in this video, we talked about something called a topology of C. Topology of C is basically we have identified which sets are the open sets in C, closed sets in C, connected sets in C, or the boundary of C. So we'll call this basic idea as the topology of C. So how does the landscape looks like? Thank you.